And we're live. Okay, so we're going to do the warm-up together. This should be a pretty easy one. So if you're struggling with this, then, man, when we left trig proofs and we kind of started, we've done 4 examples. You haven't been on board with that. You need to make sure that you're really, really paying attention, okay? Average rate of change, average rate of change, average rate of change. How do we find average rate of change? You can just tell me the initials if you want. DQ, thank you. Average rate of change is DQ, which stands for difference quotient, right? It's just the change in the y over the change in the x. So from -1 to 3, that's going to be f of 3 minus f of -1. So you want to make sure you get in the habit again of doing the larger x value first, because if you do that, the numerator becomes the displacement when you start looking at motion applications all over the change in the corresponding x values. So there's the difference quotient setup. And on any quiz or test that we take on this, I would expect to see the difference quotient. Now to evaluate the numerator, we plug in a 3. 3 squared is 9 times 2 is 18 minus 1 is 17. Minus you plug in a -1, you get 1 times 2 is 2 minus 1 is 1. All over 3 plus 1 is 4. So you get 16/4. This is known also as 4. Okay, there you go. So 4 is not only the average rate of change, it is also the slope of the what line? Secant line. Slope of the secant line. So if you want to see graphically what it is that we did, 2x squared minus 1, that's one that you all should be able to sketch. There's -1. It looks like that, looks like that. And we're going from -1, which we plugged in to get y value of 1, to 3, which would be something like that. And what we just found is the slope of that line right there. So on average, to get from this point here, on the left to that point there, we go up 4 over 1, up 4 over 1, up 4 over 1, up 4 over 1. But, of course, that's not how we actually got there. We actually went down first, and then we came back up. And we had to come up a little bit faster to make up time because we spent all that time initially going down instead of up, right? Average rate of change. Nice tennis ball. Okay, any questions on the warm-up? Okay, well, then let's get back to the thick of it, right? We were on example, we just finished example 4. Okay, cool. So now we're on example 5. Thank you. You don't need to know, right? Because you're a runner? Okay. All right. Example 5, it says, if f of x equals x squared plus 1, find the slope of the secant line between those 2 points where h is some small delta x. After simplifying the difference quotient, analyze what happens. Oh boy, that's a lot of work. Okay. Let's return up here to x squared plus 1. Let's see what we were doing. We were ultimately interested in finding the slope of the tangent line at -3, which is the instantaneous rate of change. Because the algebra requires 2 points, we chose the point we were interested in, and we chose this other point. And the idea is, as this point moves closer and closer and closer and closer to -3, the secant lines are going to be approaching the tangent lines. Okay? So as long as we have 2 points, we can still use the algebra formula. But if those 2 points are so close together that they're almost indistinguishable from each other, let's say they differ by only like a gazillionth of a point, right? Like -3 and -2.9. Right? Those points are really close together. 9, right? One more. Sorry. Now they're even closer. But there's still two distinct points. So if we found the average rate of change between those 2 points, it would essentially be the slope of the tangent line, right? So how can we then take that process that we now understand and kind of do it abstractly so that we won't actually have to do these arduous calculations? This is what Galileo was doing. Arduous calculations, trying to find how fast the balls were rolling down the inclined plane. He measured their position, and then he let a little bit of time pass, and he measured their position again. And he found their average rate of change of position over that tiny small interval to try to approximate their instantaneous speed. Okay? So he was kind of laying the groundwork for calculus, but he never did calculus. Calculus is as easy as, oh, boom, you want to know how fast it's going at this point? Boom, just plug it in, and presto magic. You now have its instantaneous velocity, okay? So we want to kind of see how they went about doing that. So that's what example 5 is kind of leading us towards. Let's go ahead and sketch the graph of x squared plus 1 again. Plus 1, okay, so there is the y-intercept again, and it opens up. Still smiling, because it's still in a math class, right? All right, so find the slope of the secant line between negative 310. So that's the same point that we've been looking at. We're still interested in finding the slope at negative 3, and of course the y value is 10. And now some other point that is negative 3 plus h, f of negative 3 plus h. What is that? Well, we're going to let h essentially equal some small change in x, right? It's going to be some small horizontal distance. All right, so I'm going to go ahead and just say, just for the sake of simplicity, that I'm going to choose another point right here, and I'm going to call this distance h units, and so that point there would be negative 3 plus h. Would you agree? I don't know what h is. I'm just defining h to be the distance between negative 3, the point I'm interested in, and the other point that I have to use because of the algebra. So then this point up here, if I go straight up, that's going to be f of negative 3 plus h. Yes, yes? Yes. Okay. So now that I have my 2 points, let's go ahead and write the equation for the slope of that secant line. All right. So here it's going to be the slope of the secant line, m. It's going to be the average rate of change. So just like we did in the warm-up, it's going to be f of negative 3 plus h minus f of negative 3 all over the change in the corresponding x values, negative 3 plus h minus negative 3. That's called the what quotient? The difference quotient, not the dairy quotient, right? Okay. Let's go ahead and evaluate it. How do I evaluate functions if I know their input? If I know the input and I know what the function is, it's just a matter of plugging in, right? So let's do that. If I plug in a negative 3 plus h into x squared plus 1 for x, I get the following. I get x squared plus 1, which will be negative 3 plus h. All right, so there's the first term in the numerator. Minus, if I plug in a negative 3, I kind of already know it's 10, but I'll just do the same thing, negative 3 squared plus 1. So you see what I did there? It's just input squared plus 1 minus input squared plus 1. All over, let's go ahead and simplify the denominator now. What happens with your negative 3's? They cancel, right? And we're just left with h. Okay, so this right here is still the difference quotient. It's still delta y over delta x. By the way, what did I say delta x was? It's h, right? So there it is. It's delta y, the change in the y values, over delta x. But instead of delta x, which is a compound variable, we'll just use h. H for some small distance between negative 3 and the other point that we have to use. Now, y'all should recognize that right there from the beginning of the year. A problem like that made its way onto like 3 consecutive tests, right? You remember that? I called it my favorite problem. It's still my favorite problem. Why was it my favorite problem? Not only because the algebra is so wonderful, but because of how it's related to the genesis of calculus. Wow. Okay. So we're still finding the slope of the secant line. Let's go ahead and expand this out now. Square multiplied over square. Square multiplied over square. So we get 9. Multiply and double, you get negative 6h, and then plus h squared. And then I got the plus 1. So there's the first bracket. And this will be minus, negative 3 squared is 9 plus 1 is 10, so it's minus 10. All over h. All right, so now let's see what happens in the top. We got 9 plus 1, that is 10, minus 10. Those cancel, right? And what are we left with? We're left with just negative 6h plus h squared. Hey, the remaining 2 terms both have a what in it? An h. So if you remember what we did back in my favorite problem days, we would then factor out that h, and that leaves us with, I'll write it in descending order, h minus 6. Now notice at this point, h can't equal 0, right? What happens if you plugged in a 0 for h at this point? Yeah, you get 0 over 0. And you can't divide by 0. Now, what does that mean in terms of my 2 points? If h were actually 0, would I still have 2 points? No. If h is 0, then I have 1 point. Right? And I'm back to the same problem of, I need 2 points. And you can see in the calculations, clearly, that h can't equal 0, because you get division by 0. But what do we know from our experience with getting zeros in denominators? If we get a 0 in the denominator but not the numerator, it's a vertical asymptote. It's undefined. But what happens if we get a 0 in the top and the bottom? What exists there? There's a hole, right? And if you remember from our studies of the limit, when there's a hole, the function value doesn't exist, but the limit does, right? In other words, we can find the y value of the hole. We can find the y value of the hole. How do we do that? We just factor out the piece that's giving us the 0 over 0 and evaluate what we're left with. And we're left with h minus 6. Whoa, wait, hold on. So you're telling me that the slope of the secant line between the point negative 310 and some other point that's h units away from negative 3, the slope of that secant line is h minus 6? Yeah. Yeah. So remember up here we did all those calculations? They were arduous, right? Setting it up, right? And then having to plug in f of 5. What is that? Okay, 26. Blah, blah, blah. You mean to tell me that I could just use the formula slope equals h minus 6 on all those points? And the answer is, yeah, you could. So remember, what is h? H is your delta x, right? Well, where is our delta x found in all of these calculations? In the denominator. That's how far apart that second point was from the point of interest. So let's see. On part A, what would be the slope of the secant line between negative 3 and 5? Well, let's try it out. If h is equal to 8, I get the slope is 8 minus 6, which is 2. Is that the same answer we got earlier? Holy moly smokers, it is. What calculation was easier? 8 minus 6 or f of 5 minus, you don't have to answer that, okay? Because it's like so no-braining, duh, all right? Let's see if it works here. It works once, may not work again. What are the odds? Let's see, h minus 6. Well, in this case, when h is equal to what? How far apart were the two x values? 5, okay? Apparently, according to this calculation that we just did, that would be equivalent to 5 minus 6, which is negative 1. Surely that can't be this. It is the same. It is the same. Wow. Let's try this one. Okay, so when h equals 3, the slope should be 3 minus 6, which is negative. Holy moly. We are on to something here. We are on to something. Let's try this one. Okay, if it works this time, I'm going to package it and sell it, right? The slope is 1 minus 6, which is, oh my gosh. All right, who's buying? Who's buying? This is wonderful stuff. That sure saves a whole lot of work on the back end, right? If we're trying to find average rates of change between negative 3 and some other point that's h units away. Why didn't we think of that first? Why didn't y'all mention that when we did example 4 the first time? Why didn't you raise your hand and say, excuse me, sir, shouldn't we do it as a variable first and create a formula into which we could then plug on the back end, making our calculations much more easy? That way we're more efficient, so there's less downtime between picking up our phone. Remember that? No one said that. No one brought that up. Why? I'm looking at y'all now. Why did y'all not bring that up? You didn't? Oh my gosh! You know what? I didn't either. I did not either. But you know who did think about it? Connor? Did you think about it? Oh, are you pointing at Maldonado? Like over, Connor? You like in a little arc with your finger. Oh, yeah, Maldonado. Did you think about it? Oh, like way over to Hank. Hank, did Hank think about it? No. Okay. You got to do like the guy that yodels. You got to kind of have to go up when you do it, right? Are you talking about this guy? Shirt? I don't think he's wearing a shirt. I think it's more like a cowl. All right? Some robe. Yes, the people who did think of this were Gottfried Wilhelm Leibniz and, yeah, you could point to that guy too, right? Isaac Newton. You know who did not think of this, unfortunately? Don't be pointing to people now, Thornhill. Galileo. As brilliant as he was, right? Galileo did not think to do this. Because if Galileo had thought to do this, he would have discovered calculus. All right? Because this has the seed to calculus. So here's the idea. Wow. What am I interested in? I forgot. I'm just so overwhelmed now. Because this is beautiful. I'm interested in the slope of that tangent line at -3. Let me move it into position there. Whoops. There it is. I want the slope of that tangent line. How close can that other point that we have to use be to -3 without being -3? How close can it get? Infinitely close, right? And so the distance between them can be infinitely small, and we call that infinitesimal, right? If something is infinitely small, we call it infinitesimally small, and that's exactly why this guy, to whom Thornhill was pointing, called his method the method of infinitesimals, Leibniz. Okay, so h can't equal 0, right? Because if h is 0, how many points do we have? 1 point instead of 2. So what's the point of doing that, right? There's no point. Well, there is 1 point, but we're missing 1 point also, right? Okay, so, but we know about the limit, and we know how to take it, and we know that if there's a hole, we can find, bless you, the y value of the limit, bless you. What happens as h approaches 0? As h approaches 0, that second point that we have to use does what? It approaches the point we're interested in. As h approaches 0. I wonder what happens to this expression that we just used and verified. I wonder what happens to it as h goes to 0. Let's see. What would be the limit as h, the distance betwixt the 2 points, as it approaches 0, not equals 0, but approaches 0 of h minus 6? Well, we know that it can equal 0, but remember, once we divide out the 0 over 0, we can use what's left by direct substitution to find the y value of the forbidden hole, right? So we've already divided out the 0 over 0. So what happens if we plug in a 0 right there for h? We get -6. Galileo just turned over in his grave. He did. Did you feel it? We just got -6. As h goes to 0, this expression gets closer and closer and closer and closer and closer to -6. Approaching -6. So even though h can't equal 0, the writing's on the wall. We can see where it's going. It's going to -6. So guess what the slope of the tangent line is at that single point? Guess what it is? It is -6. That is in fact the slope of the tangent line. So Leibniz found that. Newton also found it, because it's not just the slope of the tangent line, it is the instantaneous rate of change of that function at that moment. So if we were measuring the position of an object at this point along the curve x squared plus 1, we would say its velocity, its instantaneous velocity at that point is -6. If it looked down at its speedometer as it was traveling along that curve, at that moment, at that instant, it would say -6 feet per second or meters per hour or whatever you measure it in. Right? Wow. At that exact moment in time, at t, let's call it, time equals -3, its position is decreasing by 6 feet per second. Wow. That's awesome. That's how you cleverly circumvent meeting 2 points. Okay? Now, that's not actually how they did it, because they didn't have the limit in either one of their calculations. But they had the idea of the limit, okay? Leibniz called it infinitesimally, so he said, as it gets infinitely small, it approaches -6, but he didn't use the limit. And then Newton didn't use the limit. He just divided by 0. He just said, you say I can't divide by 0? Well, I'm Isaac freaking Newton. I divided by 0. Deal with it. And I was like, okay, all right, we'll deal with it. All right. Why does it work? I don't know. I don't know, but it works. So just Newton, right? And then later on it came that, oh, he really, okay, we don't know how he did it. Okay, and Chuck Norris is like, I know how, right? I did it too. I'm like, okay, you go Chuck Norris. Those are the only 2 people that I know that have ever divided by 0 successfully. All right, that's pretty awesome. Now, what if I wanted to find how fast that function was changing at not -3, but, oh, I don't know, at 2? Guess what I'd have to do? I'd have to do that all over again. That's a lot of work. That's a lot of work. So the good news is we have the idea of how it works, right? We define an arbitrary point in terms of its distance away from the one we are interested in. But it only works for that function at that point. If I wanted to do it at a different point, I'd have to set it up again. And if I wanted to do it for a different function, I'd have to do that work for another function. So is there a way that we can generalize it so that it's a routine process for any function at any point? And now's y'all's chance to speak up and come up with that great idea that y'all didn't have back here on example 4. Is there a way to do that? Huh? Yes, it is so intimately related to the equation that I love. My favorite equation. It is. It absolutely is. Okay, so let's go ahead and do it one more time, though, before we get too abstract. Let's just say I want to do the same thing at x equals 2. All right, so I want to know, let's call this 2. I want to know what the slope of that line is right there. All right, now we could use symmetry, right? If the slope at -3 is -6, what do you think the slope of this function is at +3? +6, right, by y-axis symmetry. So if I want to find it at 2, which is to the left of 3, do you think the slope is going to be bigger than 6 or smaller than 6? It should be smaller than 6 because to the left, the graph is not increasing as quickly. The slope is smaller. So I know it should be some number smaller than 6. But is it 5.9 or is it -1,000,000? Well, it's not negative. It's some positive number, silly. Let's find it. Let's find let's create our 2 points. The point of interest is 2, f of 2, which we can find pretty easily. And the other point that we're going to use, wink, wink, the other point is 2 plus h, f of 2 plus h, right? Don't tell anyone it's not an actual point, okay? It's just another arbitrary point that's h units away. So those are our 2 points. So just like in the warm-up, we'll find the slope. It's going to be f of 2 plus h minus f of 2 all over 2 plus h minus 2. So it kind of has the seeds again of my favorite problem. Now we need to evaluate both terms in the numerator by plugging those inputs into our function. So at this point, this could work for any function, right? If our function was the square root of x or sine of x, at this point it doesn't really matter. It only matters when you start evaluating the numerator and you start plugging these inputs into your particular function. So for us, it's going to be 2 plus h quantity squared plus 1, BP brackets, minus 2 squared plus 1. All over, that becomes h. It should always end up being h in the denominator. And there's my favorite problem. All right, so that's just the what quotient? Difference quotient. That's just the difference what? Quotient. Okay, cool. So let's go ahead and expand it out. Square multiplied by square, we get 4 plus 2h doubled is 4h plus h squared minus 2 squared plus 1 is 5 all over h plus 1. Oop, hang on. Oop, yeah, I forgot the plus 1 over here. 4 plus 4h plus h squared plus 1. Okay, don't forget the plus 1. And then minus 2 squared, which is 4, plus 1 is 5. Okay, so if you set it up correctly, just like it was back in the day before you had no idea, before you had any idea of what it was, everything without an h should cancel, leaving everything on the top that's left with an h that you could then factor out, and the magical part, divide out. So let's do that. That's going to be 4 plus 1 is 5 minus 5 is 0. Factor out the h, and you're left with h plus 4. And then divide that by h. Here we go. Ready? H can't be 0, right? It can't be 0, because then you only have 1 point. But because I know there's a hole there, as long as h is not 0, I can use that formula to find the slope of the secant line between the point 2 comma f of 2 and some other point that is h units away. All right, so I'm not interested, though, in the secant line slope. I want the tangent line slope. So what can I do with that expression? I can now take the limit as h goes to 0 of that secant line expression. And, of course, we know that we can use direct substitution to evaluate it, but when we do that, we're still not claiming that h is 0, are we? We know h can't be 0, okay? But we know from our past experiences that if we divide out the whole, we can use direct substitution on what's left to give us the y value of the function that doesn't exist. And so we get 4. And there you go. Galileo just grumbled again. Did you hear him? Like, "Rrr!" Guess what the slope of the tangent line is? At 2. You don't have to guess. It's 4. And that's right in the wheelhouse of where we thought it would be, right? We knew it was going to be some positive number less than 6. So that's the instantaneous rate of change there. So we can do the same thing now for any point along this graph, right? Any point, do it the exact same way. Just set up your 2 ordered pairs like we did. Find the average rate of change, simplify, divide out the h's, and then the magical part is letting h not equal 0, but what? Approach 0. Yeah. Remember, the limit is a notion of motion. It's the idea of getting closer and closer and closer and closer to something without actually getting there, but then seeing the writing on the wall, right? Getting right up against the electrical fence almost at Area 51 so you can see the aliens inside, right? But you don't want to touch the fence because then, right, deadly force. But if you get really, really close, you can kind of see the aliens, right? Sweet. All right, that's, does anyone find that, like, incredibly fascinating? Besides me. Yes, okay, 2, 3, okay. For the record, 2.5 hands went up, for the record. 2 1/2, 3 1/2 hands. No, that was another half, so 3 hands. Oh, double hand! All right. Yeah. All right. And not only is it fascinating, but to think that, like, 2 dudes separately, motivated by separate things in 2 different parts of the world at roughly the same time, came up with this idea independently, right? The world at that moment was ready for calculus. And so it came into existence. Okay, sweet. So very important idea. Very important idea, as I'm just reading. Okay. The slope of the tangent line, not the secant line, to the graph of any function at the point x comma f of x. Here's how we're going to make it more general. Instead of using x equals 2 and x equals -3, we're just going to let it equal x, where x could be what? Any x value, right? For any function f of x, the slope of the tangent line for any function f of x at any point x f of x is going to be the following. We take the point x f of x, and then we take the point that is h units away from there, x plus h, f of x plus h. And we set up the difference quotient, right? That's what that is. That's the difference quotient, the dq. No calculus there, right? That's just algebra. Change in y over the change in the corresponding x. But what's the magical part? What are we going to do? We're going to let h, the distance between the 2 points, go to what? 0. And that forces the 2 points to converge to each other. And that magically turns a secant line into a tangent line. It turns an average rate of change into a instantaneous rate of change. Okay? We call that new function that we're going to get, we call that f prime. That's how we read it. We call it f prime of x. It's another function, but it's related to f. So we use the same name, but we give it a prime to show that it's not the same function, but related to. It's f prime of x. And that is what's known to us, not Galileo, poor guy. At least he knew the sun was the center of our solar system, right? He had that going for him. We call that the derivative function. So what's the derivative function? F prime. And what does that function give us? It gives us two things. It gives us either the slope of the what line? Tangent line, or from the Newtonian perspective, it gives us the what rate of change? Instantaneous. Yes. All right. So your kinematic equations, if you have a function x of t, if you have a function x of t in kinematics, that gives you the position of an object. Or it could be y of t, either one. One is measuring horizontal position, one's measuring vertical position. If you want to know what the instantaneous rate of change is of position, that is, you want to know what the instantaneous velocity is, all you got to do is take the derivative of that function, and you get a brand new function, which for kinematics is called velocity. That's awesome. It turns out the derivative of the position function is the velocity function. And let's say you're watching the velocities change. You're like, ooh, look at his velocities change, right? If some guy's at a stoplight and the light turns green, his velocities are going to increase, right? Which means he's watching, accelerating. So if you want to know how the velocities are changing at any moment in time, and not over an interval of time, but at any instant, you need the derivative of velocity, which is called acceleration. The instantaneous rate of change of velocity is the instantaneous acceleration. And that's how your kinematic equations came into existence, kind of, right? Position's derivative is velocity. Velocity's derivative is acceleration. So really, all you had to do is memorize the position equation, and then if you wanted to get the velocity equation, all you have to do is set up this and evaluate it. Now, that's pretty special, because it works for any function at any value of x. But guess what? This, when it came into existence, was fabulous. But there's actually an easier way now to get the derivative. Okay? Once this process became known, people started again looking for shortcuts, right? It's human nature to look for shortcuts. It's not being lazy if you actually work at finding a shortcut. It's called being efficient, right? There's a difference, right? Lazy is just like, whatever, right? But being intellectually lazy is like, I gotta find a shorter way to do that, right? And so there is a shorter way to do this. But we're not going to get there just yet. Right now we're just going to marvel at the ingenuity of people, okay? So whenever you then calculate the derivative of a function, which we're going to do probably tomorrow, the process is called differentiation. Differentiation. Now, in the educational world, unfortunately, differentiation does not mean, oh, you're computing a derivative? No, we're just changing the curriculum so that everybody in class learns at their own rate, right? I'm differentiating. I'm making this guy's assignment easier because he's lazy, and this guy over here, I'm going to give him tons of work because he's GT, right? So that's differentiation. But in this class now, differentiation is we're finding derivatives, and we're all doing it. We're all going to be finding derivatives. I'm not going to let somebody find not a derivative and somebody find like 100 derivatives, right? We're not going to differentiate that way. We're going to be using differentiation to find what? Derivatives. And what do derivatives again represent? Instantaneous rate of change, that's Newtonian, or Leibnizian, slope of the tangent line. Okay. So there's all that stuff down there. There are other equivalent notations for the derivative besides f prime. Of course, if we name the function y instead of f of x, y prime, and get this. This is the last thing we're going to finish with. This is beautiful too. dy over dx, or we just call that dy dx. That also means f prime or y prime. Okay? We read that as the derivative of y with respect to x, or the differential of y divided by the differential of x. That's Leibniz notation. If you remember, I told you Newton got all the credit for calculus, but we don't use his notation. Leibniz didn't get credit in his day, but he gets the last laugh. We use his notation. Now, This is pretty cool. I like Leibniz notation a lot because remember, slope, algebra slope, was the difference quotient, right? And we can summarize or abbreviate the difference quotient as triangle y over triangle x, right? What does the triangle mean? Delta. Delta y over delta x means measurable change in y divided by a measurable change in x. Notice how similar that is to dy over dx. It preserves the slopey feel, doesn't it? But dy, unlike delta y, dy is so small, it's non-measurable. dx is so small, it's not measurable. They're infinitesimally small. So Leibniz kind of piggybacked on the algebra slope notation, delta y over delta x, replaced the delta with a d, which means differential. And we have a new notation for something that is still a slope, but at a point, not over an interval. All right, fantastic. We'll pick up with example 7 tomorrow. Enjoy the rest of your shrimping day.